Hi guys, how are you? Today we've got a pretty cool speaker lined up for you today. He used to work at ESOC. He's also an ex-Australian, but still an Australian. And he's also built a robot lander that could fly to a comet and essentially harpoon it. But more about that later. And this is Warwick Holmes. So he's going to be talking to about a few things, and we're going to be having a discussion afterwards that he sort of hasn't done in Australia before anyway, I know that. So before we begin, I'd just like to thank Fishburners as well for giving us this space. Really awesome of them, really nice of them. And they also give us a free beer and some of the food and stuff like that. So without further ado, I'll hand it over to Warwick. Thank you.
Okay, thank you, Sebastian. Thank you, Tom, for inviting me this evening to Fishburners. This presentation on behalf of OrbitOz. So tonight I'll be presenting the Rosetta mission, the European Space Agency's Rosetta mission to Comet 67B. So, to start the presentation, I'm going to show you a 1-minute video, which is the introduction to a documentary that was made by the Discovery Channel, where they had some cameras in the control centre in Darmstadt in Germany just a few minutes after the landing on the Comet. And I'm just going to show this to you just to give you a feel for the enthusiasm and the excitement of that event, and then I'm going to go into the presentation after that.
This is it! You are watching history being made. The first ever landing on a comet. I'm Dan Riskin. I'm in the most exciting place on the planet right now, the European Space Agency in Darmstadt, Germany. And this crowd is cheering because an incredible group of scientists just put a lander on the surface of a moving comet. Now they made it look easy, but this mission and what it's about to do are groundbreaking.
Is it real? Are we there?
This is a big step for human civilization. It could revolutionize everything. Desperate to reveal life's origins, they're a treasure chest with a view back in time. A quest decades in the making.
It's one of the most difficult things you can try.
An epic adventure to chase down a dragon and ride on its back.
Cherry on the top is really the landing.
Touching down, it's all down to Isaac Newton now, where no one has landed before. We're moving in for the kiss. But first, separation anxiety. 7 agonizing hours.
I don't have any fingernails. They've gone already.
We are on the comet. A comet, up close with unprecedented clarity.
We're making history here. This is one for the record books.
We know the world is watching this mission.
Okay, so you can see the event was extremely exciting, and that just gives you a flavour for how amazing the achievement was in the action of the first landing. So tonight there are 100 slides. It's a long presentation. I'm going to go through them in roughly 1 hour. But I'm going to give you a full overview of how the spacecraft was built, how the mission was designed, the images and the science that were achieved on the comet and in orbit around it, and some of the scientific findings that were made as a result of that. So the fundamental question is, why do we want to go to a comet? What's so special about a comet which is different from all the other bodies of our solar system? We've visited most of the planets, but we've never visited a comet before. It was the first time ever in the history of space exploration, and the first attempt ever to go into orbit and try to land at the same time, or the same mission, I should say, on a comet. The reason we want to visit one is comets are completely different than all other bodies in the solar system in that they have not been affected by the heat of the sun or the heat of the formation of planets. So when the planets are formed, they collapse in the gravity and they get incredibly hot. The core of the Earth today is molten bedrock magma, which is still molten after 4.6 billion years. And that shows the kinetic energy in the heat and the radiation decay, which is causing the centre of the Earth to still be molten. Comets were formed at the very, very beginning of our solar system. So So here on the outside, this is an image or a graphic of what we believe the solar system looked like 4.5 billion years ago. The problem is that this image is actually too late in the sense that the sun has actually already formed. Here in the middle, and some planets have already formed. Comets actually formed before the sun and the planets were created. There was just a large swirling disk of gas and dust before the sun was formed, and the chemistry associated with that collapse and that condensation of the early dust of our solar system was when comets were first made. So there's chemistry going on in comets which is completely different than any other body of our solar system. And they've basically preserved the chemistry of the formation of our planets from 4.6 billion years ago. It's like having a piece of paper and burning it. So all of the sun and the planets that we have today are all effectively burnt pieces of paper. We've never seen a white sheet of paper in the chemistry of our solar system. A comet is a white sheet of paper. It's never been affected by heat. It's never been burnt. The chemistry has never been transformed in a way that it can never be reversed. So that's the interest of going to a comet. So scientists want to answer the question, how do we get from this is a nebula of an exploded star, a supernova nebula, the remnant of a star which has exploded. And huge amounts of gas and dust and elements are generated, and this then condenses and starts to swirl around their disk to form a new solar system. So the death of one star is the birth of another one. So how do we get from this great ball of gas and dust to planet Earth? That green arrow, that process involves comets. How do we get from planet Earth to this? Intelligent life. There you are. Now, those two green arrows, the process involves comets. And that's what I'm going to show you. So, the very beginning of our solar system, cometary material, which had first formed as a large disk, started to coalesce and collapse under gravity to form our planets. And so this is a comet coming in, hitting a proto-Earth, an early Earth 4.6 billion years ago, which again has this red hot molten magma as the surface, which then eventually cooled down and formed the crust that we see today. So the first process was the formation of planets using the gravitational collapse of cometary material to make the first planets, and also the Sun. There was then a second stage, where comets came in 1.3 billion years later, and brought the material that made our oceans, the waters of the oceans, and the early carbon chemistry that helped form life on Earth. And the way we know that, if you look at the Moon today, you can see millions of craters on the Moon. So obviously the Moon was formed, and something came afterwards to create the millions of craters on the Moon. And that process was this secondary bombardment of cometary material that was caused by a complex gravitational interaction with the outer planets. Jupiter, Saturn, Uranus, and Neptune actually changed positions in our outer solar system, and that disturbance brought in another wave of comets. A bit complex, but this is the theory. Anyway, the point is there was definitely a secondary bombardment because the Earth had cooled down, and then the secondary phase left the water of the oceans. There's no water on the Moon because it doesn't have the gravity to hold water. But we see the evidence of the bombardment. There are no craters on the Earth because they've been rubbed out by plate tectonics and by weather. But the water was left behind. So there was this sort of two-stage bombardment in the formation of the solar system that helped create the Earth in the first place, then the water and the carbon chemistry that very quickly formed life. It was 200 million years after the water of the Earth was brought, life was formed. And that is a ridiculously short period of time for life to evolve from just water with no other help. And the help were amino acids that came from a comet. There's a meteorite which hit Australia in Murchison in Victoria, and this is an image of the inside of it. And this is an extremely unusual meteorite, in that inside it were 100 amino acids were found, in fact more than 100 now. And it had an unusual smell. When the people of Murchison in Victoria saw it come in, and they actually picked up these black pieces of comet, it smelled like bitumen and methylated spirits. There was an organic smell to this rock. So they then had some very complex analysing processes where they can actually look inside the Murchison meteorite, and they've found more than 100 amino acids. And the ones that we can see here are guanine and adenine in the southern protein. These are the same amino acids in our human bodies. These are the nucleotides that form the RNA and DNA sequences of human genetic chemistry. very, very first molecules that help form cells with RNA and DNA came from comets. We have found that inside Murchison, and we're now going on 67 to prove that directly in situ the same chemistry is on the comets as well. So this is the interesting comets. Water and life. And that's what we said in the introduction video as well. So how do we do that? It's all very well and good. How do we get to a comet? So the first thing to do is plan a trajectory. Can we even get to a comet? Now, as in that first slide I showed you, it was on the outer edges of the solar system, and they got brought in with gravity and surfaces. They're very far out, and they're travelling very fast in energy terms. So we had designed a trajectory to get out to a comet, and try then to match the speed so that we could land on it. You can't land at a high speed rocket because it'll just crash into it. So we had to match the speed of the comet and then attempt to land in. So this has never been done before. This is what the true challenge of the Rosetta mission was to try to actually get even at the same speed as the comet. So this is how we do it. This is a video showing the trajectory around the solar system from Rosetta to actually catch the comet. So the blue line here is the Earth, and the white line leading it is Rosetta. So this is the Rosetta trajectory on the 2nd of March 2004. We left the Earth, and we came back in again, and we used what we call a gravity assist, where the actual speed of the Earth around the Sun was accelerated the spacecraft by an extra 15,000 kilometers an hour. We went further out, we came back again. We used Mars gravity assist to change our orbit to come into the Earth for a second time, for a second gravity assist. Another 15,000 kilometers an hour for nothing. Just being at the right place at the right time, we get an extra 15,000. We're now coming out, we go through the asteroid belt, I'll show you those images coming out. And then we come in again for our third and final gravity assist. And this is like a free lunch. If you're in the right place at the right time, you get an extra 15,000 kilometers an hour for nothing. It's like being on a skateboard, and the bus comes past, and it's going in the right direction. You grab the back of the bus, and you get accelerated for nothing. You let go of the bus, and you go down the road. Another bus comes along, you grab that one, and you get a free ride again. So long as the bus is going in the right direction, in the right trajectory, you can grab onto the bus with your skateboard. Well, this is what we're doing with gravity and the planetary orbits of the solar system. We're actually now matching the orbital speed and the trajectory of the comet now. And this is where we did our first encounter in orbit around 67 feet. We arrived on the 6th of August. We started mapping, looking for a landing spot. On the 12th of November 2014, we actually did the lander delivery and the actual landing. Just as the comet was becoming active from the heat from the Sun. So we come in now and we're at what we call the perihelion, the closest point to the Sun. It's on the 13th of August this year, so we just passed. And then the mission, it says here, ends in December, but we've now extended it by an extra 9 months. Because we've got so much fuel on board, the mission's been so successful, we've actually got enough fuel to continue following the spacecraft, the comet, for another 9 months. Further than expected. At the end of that, we will actually be putting Rosetta down onto the surface of the comet as well as the lander. He's already done that. Okay, so what does this magnificent spacecraft look like? Well, this is it. So we've got here the main spacecraft here. These wingtips, from wingtip to wingtip is 32 meters. There's 64 square meters of solar panels. This is the first time ever a solar panel spacecraft has been used for extra in-space exploration of the solar system. There's a reason for that, because we didn't want to use nuclear fuels, because we were doing the Earth gravity assist. And if we're doing the Earth gravity assist, we didn't want that to go wrong, and put plutonium into the upper atmosphere. So we use solar power. The body of the spacecraft is 2 by 2 by 2 meters, so it's 8 cubic meters of the spacecraft, holding all the electronics and the instruments for going in orbit around the comet. And this is a 2.2 meter high gain antenna which we use for doing transmissions to and from Earth. This is a view from the other side, and here we can see the Philae lander, which is about the size of a washing machine. It weighs about 100 kilograms. The spacecraft weighs 3 tons, and it's fully fueled. More than half of that mass is actually fuel, chemical fuel. But the little lander is only 100 kilograms, and that's now down on the surface of the comet. This is a graphic just showing some of the instruments on Rosetta, which we use in orbit around the comet. There's 21 instruments in total, 11 on Rosetta, and 10 on the lander. I won't discuss all this because the presentation will take 4 hours. Okay, so this is an image of the lander, free flying, so it's got a little tripod landing system, and some of the features here are, you can see these footpads here have a microphone and a speaker in each of the footpads, so that when you come into contact with the comet, we can do acoustic sounding. We use some seismology, a bit like a sonar or a submarine. We pick audio signals into the comet, and we can actually look at the structure inside the comet using audio. We have these antennas, which is for doing RF tomography. That's like brain scan. We can do a scan through the comet as well, and the orbiter is going around the comet. There's 10 other instruments here, including a mass spectrometer, gas chromatography, some of the most advanced instruments possibly imagined. In fact, there are city hospitals that would be jealous of the instruments in this little box. And this is the names of them here, which again I won't go through it too long. Now this is an interesting comparison. I took this slide from a NASA colleague who was trying to compare the complexity of the ESA mission to the earlier NASA missions. And the Voyager one was a complex mission. That's where they flew past 7 planets about 30 or 40 years ago. And he said that was a difficult mission. The second mission that he was comparing was the Mars rover mission. They left that little road down on Mars and we drive around Mars, and he said that's a very difficult mission. So comparing those to what ESA had achieved, like landing on the comet, he said, well, it's ridiculously and absurdly difficult. In fact, I heard another colleague say, he said that when ESA achieved that landing on the comet, they basically turned probability theory into bullshit. I have to agree with it. So this is just a very quick slide showing how Rosetta was built. So there's an industrial organisation of what was then 20 nations who were member states of the ESA, European Space Agency. The whole project from the very first meeting to where we are today was 25 years. So the very first idea of doing this was 25 years ago, first meeting. 18 nations, were involved, not 20. 2,000 people in total from the very beginning to where we are today, but only about 40 were actually involved in the final building of the spacecraft. I was lucky to be on that scene. $2 billion Australian dollars is the total cost from that first meeting 25 years ago to where we are today. To put that into context, the Australian military spent $30 billion a year, so this entire mission would have been paid for by the Australian government, military budget, in 3 weeks. Just as a comparison. A lot of people saying, is it worth it? Well, when you look at those comparisons, I think this is a very good outcome for that cost. And 70 contractors. Okay, so this is a photo of me 15 years ago, when we started to build the very first flight model. This is in Italy, in Turin, where the company, the industrial contractor Linea Lazio, were the contractors for building the spacecraft. And this is a photo in the European Space Agency when we were doing the final testing of the spacecraft. Now these are images of me 15 years ago, so you can see what the averages of 15 years in the space industry do. Aging. Okay, so this is a photo of me beside the lander. And this was an interesting shot because on the left here, are these little red wires here connected to orbital accelerometers. This is a vibration test of the lander to see that it survived the vibration of the launch of the Ariane 5 rocket. And I had to connect these things onto the legs here of the lander. And at the time, I just didn't even think about it, but those legs are now touching the comet. And I was touching those here on the Earth when they were doing testing. I just didn't even think about that, which I sort of regret now. But at that moment, I wish I'd thought more carefully to realise that this little thing, which I'm touching right now, will one day potentially be on the surface of the comet, which it now is. Now, it wasn't an individual effort by any means, it was a team. And the whole success of Rosetta was extremely good team management. Having lots of incredibly clever people to work together, which is quite difficult sometimes. But this is a team of 40 engineers in total that were involved in doing the final building. So this, you can see a little fillet on the back here. Spacecraft is completely wrapped in black and alive for thermal reasons. Okay. Now I took 11 hours of videos of when I was building Rosetta because I just put the camera in the corner of the room and just turned a video on. And I took a few little snapshots here which I've just extracted just to show you how we did it in clean room. So this is the label of the lander. This is SSP, which is the Surface Science Package. That's what we call the lander. FM flight model, and this is building a satellite system of the company that made the lander, and this is their code. So this is just to show you here, which is now not going to work. So this is the label on the lander, and you can see inside here. This is the main microprocessor. This is the flywheel that stabilizes during the landing. And this is an internal battery, which is its power source for 3 days. This is a drill, and this is just some of the internal components when we were building the actual lander. Now this is me superimposing the picture as I came into the screen to do some testing. So I actually had to do some electrical measurements on the interface connecting Philae to the Rosetta spacecraft. I was an electrical test engineer, and my main job was to verify all the electrical interfaces of the system of the spacecraft. And so everything is done, there's meticulous documentation on everything to do with the spacecraft. This is where I was going into the interface measurement. This is the drill that is now drilled into the surface of the comet. And this is the separation mechanism on which connects us to Rosetta and then pushes the lander off. Here I'm just using a digital voltmeter to measure the electrical interfaces that will one day be connected to the Rosetta spacecraft. Okay. This is the separation test of fuel A from the lander. And this is exactly the same speed that was popped off from the spacecraft in orbit around the comet. We've got an audio problem here. So, this is just some of the highlights of the different tests which we were doing. So this is a Rosetta spacecraft, just before we went down to Peru and launch site. And on the bottom here is a little lander delay again. And that's how we carried it for 10 years, a total distance of 7 billion kilometres. We carried delay to get to the comet. 4 times around the sun with those gravity suits, total distance 7 billion kilometres. This is again checking the electrical interfaces or the connection. Constant checking. 8,000 hours of testing I had to do on the spacecraft to be sure that everything was working. Most of the time it wasn't working. And this was my job, to find it and fix it. Very, very complex spacecraft, software written for the first time, thousands of mistakes. But that's why I had a job, was to find them correctly. This is a solar array deployment test. This is one of the one panel of the 2 panels of the spacecraft. We have here on a 0G rig, which is used for offsetting the effect of gravity, because in space there's no gravity, of course, and these solar panels come out very easily under no gravity force. So we have to simulate that on Earth, because the 1G effect would actually break the panels off. So we've got this very complex rig here, which is used for offloading exactly the 1G force. Switching noise you can hear are the hydraulic bearings which you use to, with almost zero friction, used to help deploy the solar panel. So this is a 32 square metre solar panel. This is one of the most expensive solar panels ever made in the history of mankind, because it had to be extremely efficient and was hundreds of millions of dollars. You can see they're also black. They're so efficient that they actually almost don't reflect any light except for the glass which you see in front. So that shows that the deployment mechanism of the solar panel in space theoretically is going to work. That's the purpose of this test. Again, after that, constant checking. Again, me with a colleague, checking all the electrical interfaces between the panels to ensure the continuity of the power is getting into the spacecraft. So what I'm just trying to show you here is a series of snippets of how rigorous the testing and the development was to be sure that this spacecraft could survive for 12 years in space without any human interaction whatsoever. Once something was launched, we could never ever touch it again. And it had to work perfectly, which I believe it has. So that process just involves thousands and thousands of hours sitting behind a computer. Probably the most boring job in the world. Okay, if you yield building the spacecraft, it's actually very interesting. But the majority of the work is actually just software. Testing thousands and thousands and thousands of routines on board the spacecraft, finding errors and correcting them. In those days, you can see we had these old video displays, so there was no flat screens in those days. This is 15 years ago. This is the high-gain antenna. Now it's sending signals from when we're out in Jupiter. The speed of light delay from this antenna to Earth is 50 minutes. So anything that happened on the spacecraft, it would take 50 minutes for that signal traveling the speed of light to get back to Earth. That's the distances involved with solar system exploration. And so we had to build in an enormous amount of intelligence into Rosetta so that it could actually look after itself. If something went wrong, if one of the fuel valves opened, it would take 100 minutes for us to do anything. 50 minutes to find out, 50 minutes to send the command back to turn the valve off. After 100 minutes, there's no fuel left. So we had to build in an enormous amount of intelligence into the spacecraft to look after itself for these critical functions. This is where I was giving the final go for launch. This is in the French Guiana, where we were doing the final countdown, and I was designated as what we call the SST, the Spacecraft System Team Leader. We were giving the final go to the microphone to jump up Germany during the countdown. So we had to give the final go to launch. And then there's an automated 15-minute sequence which gets started with no human intervention. That's the voice that you can hear in the background of all the voice communication going on around the world, different ground stations in the control center, and here the launch base in French Guiana. Okay, so that's the end of the videos. This is now just some internal views of Rosetta, just showing how complex the spacecraft is. This is a gyroscope inside, a laser gyroscope, which can measure the rotation of the spacecraft to 30 times slower than the hour hand of your watch. So if you watch your hour hand, it doesn't move very fast. It's 12 hours to do one rotation. This can measure the rotation of the whole spacecraft 30 times slower than the hour hand of your watch. This is an example of how accurate the inertial navigation is. All this silver stuff here, here this might work for some of the fuel systems on board the spacecraft. We use monomethyl hydrazine, nitrogen tetroxide, two extremely explosive fuels for moving the spacecraft around in space. One of the biggest challenges was making sure the spacecraft was going to work in the thermal extremes, because when we launched, we went in towards the sun, slightly to get the right trajectory, and then we went out to Jupiter. Now those distances mean that the solar constant changes by a factor of 25 times. So that translates to a thermal extreme of minus 170 degrees plus 150 for the spacecraft in space. Now that's a range of more than 300 degrees Celsius. So imagine if you have TV and you put it in the freezer in your kitchen. Now maybe your TV will work at 0 degrees Celsius if you're lucky. Not yet turn it on, might get an image. Put it in the oven at 300 degrees Celsius and see if your TV works. Well, it certainly won't. The spacecraft is designed to operate in those extremes for more than 12 years. And that's just another one of the challenges. Not only the autonomy, not only the complexity of your software, the distances involved, but also these thermal extremes and radiation as well. So it really was an absolute miracle of engineering that this thing worked for, given all those constraints. Now, anybody see something unusual in this picture? And Tom don't say anything, I think you know. Can anybody see something unusual on the lander?
Angles.
Who said that? $50? Absolutely correct. There is an Australian $50 note. Okay, now, I'll put that there as a science comparison, so you can see how big the lander was. Anybody has to guess how many of those you'd need to buy a lander? Well, you need a pile of 40 million of them. The lander costs about 200 million Australian dollars, which is actually quite cheap when you think about it. Yeah. So these are views inside the lander. This is one of those complex boxes of electronics I've ever seen this time in space. They've got, again, I said, mass spectrometers, aftermarket scaverometers, dust impact monitoring, 7 color panoramic cameras, acoustic sensing, RF thermography, every ology, oscopy, and ometry you can imagine is put into that box. Because if we're going to carry it for 10 years, 7 billion kilometers, at a cost of $2 billion, to land on the comet, we're going to be sure it's the best instrumentation you can imagine. And that's what it is. These little gas bubbles here are little helium reserves that you use for pushing gas through the mass spectrometers. So there's many things to do. Okay, so that's the engineering, that's how we built the spacecraft, and now we're going to launch it. So we go down to French Guiana. Now in 1 day's time, Australia will be launching its first NBN code satellite from exactly this launch pad. This is the Ariane 5. This is a dedicated launch just for us, which is on what we call a hyperbolic trajectory, which means we're working good. But the NBN code satellite will be launched into what will be a stationary transmitter. And there's 2 spacecraft, I think, you can carry. So this is exactly what we're going to see if you watch the news in 24 hours. We'll be seeing exactly this launch pad, which is where Rosetta got from. Okay, so this is the Ariane 5. This is the base. I've got a little model here. And that's me right at the bottom down here. That gives you an idea of how big that rocket is. So that little cone at the bottom is this little cone down there. So it's more than 50 meters high. Okay? This is at the top of the booster, which is this funny cone-shaped thing here. So we had to scramble all over this thing to do the electrical connections for Rosetta. Again, testing everything before we launched it. This is again that final go for the countdown. Okay, so we're off and away. This is on the 2nd of March 2004. And the operations centre in Germany, Darmstadt, Germany, is where all the signals for controlling Rosetta when it was launched came from. And that's where that video at the very beginning was made by Discovery Channel. But in the first 8 years, every single transmission to and from Rosetta went via this 35-metre dish in Australia. In New Norcia, 150 kilometres north of Perth, there's this ESA European Space Agency ground station, which is the only station that has command and control Rosetta. It's a little bit like the dish story for Apollo 11. There are all videos came by the Parkes Radio Telescope in New South Wales. Well, we've got our own dish story here at Rosetta. The majority of you in the room probably know that. And that's a bit of a shame because Australia actually had a very important role in the early part of the mission. We are every 8 hours communicating with Rosetta from Australia. So, we're off the way. We're doing that complex trajectory which I showed you earlier. And this is our flyby over Mars. And this is where we turn the cameras on delay to look down to the surface of Mars as a test object. Okay, so this is the back of the solar panel, that 32-metre panel which I showed you deploying. And this is us looking down onto the surface of Mars. And the whole lander which is then bolted onto Rosetta. So this is the first solar system selfie. There it is. We're travelling 36,000 kilometres an hour over the surface at an altitude of only 350 kilometres above the surface of Mars. If we got that long and crashed into Mars, mission over. Okay, so as we're flying past, whenever we fly past any object in the solar system, be it a planet, Earth, or Mars, or an asteroid, we turn on all our instruments and we try to calibrate them against other measurements taken from other spacecraft. So we're flying past Mars. There's been 51 missions to Mars, and so of course we know about the atmospheric components of Mars, so we turned on our cameras and we select different filters. Take different coloured images which shows different kind of gas components. So it's a good test object, and we had 17 different filters, and we used all of them to get these different images of Mars. Okay, so then we flew past 2 asteroids. This is only one of them. This is Rosetta. This is from a distance between Sydney and Perth. So the spacecraft was in Sydney, this asteroid was in Perth, and this is the quality of the images that we got flying 54,000 kilometres an hour. And that's how good the cameras are on Rosetta. So we can get that image. So imagine you're on Sydney Tower, and there was a rock in Perth. The rock is actually 100 kilometres across, so it's actually quite big. But still, to get an image like that, and across the entire diameter of Australia, it shows you how good the cameras are. Okay, so then we had to do something very unusual. I told you we had solar power, first time ever. We used solar power on a deep space planetary mission. It turned out that as we got out towards Jupiter, there wasn't enough electrical power to power the spacecraft. Now we knew that because we calculated it before that. So we'd actually planned a 2.5-year hibernation phase for Rosetta, which meant turning off absolutely everything except some heaters and 4 timers. The 4 timers were set to 80 million seconds, which is 2.5 years. And they counted out all 4 of them in parallel. Any 2 which get to 0, works the spacecraft back up again. We did it for redundancy reasons, and miraculously it worked. But the issue here was that we only had 300 watts of power, and we needed 500 as a minimum to turn the computers on. So we knew we had to turn everything on. Now, when you're at home, you turn your TV off with the remote. Your TV is not on. It's actually still on, and it's listening for you to push the button with the remote. So when you pick up the remote and click the on button, your TV is actually on, so it's listening to that button. Okay? Working for electrical signal. If you pull the plug out of the wall, your TV is completely dead. And you can push that remote button all you like, and it's not going to turn on. That's what we did to Rosetta. We turned off the receivers, we turned off the transmitters, we turned off everything. We needed to have a mechanism inside to turn it on autonomously after 80 million seconds. And luckily it worked. The problem is we had to find Rosetta again with no signal to track for 2.5 years. Now this little black dot, we're all familiar with how big the moon is in the sky. That black dot is how accurately we had to point 2 70-metre dishes to find the signal of Rosetta by just calculating where we hoped Rosetta was going to be. This is the beamwidth, or this is the size of the dot in the sky that we have to point to get the signal of Rosetta. If we were very slightly to the left, no signal. Very slightly to the right, no signal. Okay, if we didn't find it, we then start doing a spiral scan, trying to find it. We pointed there, turned on the receivers, and this is what we found. These 2 signals, this is a 70-metre dish in Canberra, and Tipindilla. This is a 70-metre dish in Goldstone in California, at a very narrow frequency. These carrier signals here can only come from one spacecraft, and that was Rosetta. So luckily, it had woken up, and we knew we had a mission. So the hibernation had worked. So hibernation was here, almost the furthest extent of the orbit. Our first orbit around the comet was here on the 6th of August. We're landing on the 12th of November. And today, we've just gone past the perihelion, which is the closest point to the Sun. And we're at this point here where actually, the comet tail is actually more active now than it was at perihelion, because there's sort of a delayed heating effect. So the tail is actually bigger, and the coma around the comet is actually larger than when we were actually at the closest point. That's because it's like this delayed heat effect. Okay? So today, 30th of September 2015, we're travelling at 116,000 kilometres an hour, which is a bit slower than the maximum speed of 123,000. Earth is 269 million kilometres away, the Sun 205, and the speed of light delay is 15 minutes. So every photo, every image, every piece of information we get from Rosetta takes 15 minutes travelling at the speed of light to get to us, which is short compared to the 15-minute delay we had at Jupiter. Still, imagine if you take a photo, and it takes 15 minutes to get the image in the back of your phone. Imagine driving your car and trying to reverse park, where you turn the steering wheel for 15 minutes to reverse the mode. 15 minutes for you to see the image of the car behind you. You can't do anything with those kind of delays. And so this is again where the complexity and software on board Rosetta is necessary to do all the work for us. Okay, so this is the very, very first image we ever saw of the comet through our star cameras, which we use to navigate. And I'd like to ask you here, can anybody here see the comet? Well, I'll help you. Just above the red dot, one star is not moving. So we're using those stars to navigate, and we know exactly what we're seeing there, and we expect to see the comet in the middle of the image, and there it was. Again, this is all just navigation mathematics. But luckily it was there, so we knew we had a mission. We found the comet, and all we had to do was hone in on that. This was the first images ever acquired of the comet. We had no idea what the nucleus of the comet looked like. We saw the tail, we knew there was a comet, because we saw this tail which is millions of kilometres long, coming from some point which is the head of the comet. We had never seen this detail before. We had no idea what the shape or the size of Comet 67B was. And this was it. And we got one hell of a shock. Because that body is an extremely strange shape. We have never seen anything like this in the solar system before. Even asteroids are roughly spherical, like potatoes, you would say. This clearly had a head and a body and a neck region. I've got here a small 3D model. This is a laser printed 3D model of the comet. And in fact, it's been confirmed by the scientists that there are actually two comets. We've got two comets for the price of one. The head and the body are actually two separate comets which were drifted and stuck together about 4.6 billion years ago. So we're very lucky that we got this very unusual object. And they said, well, look, it looks like a rubber duck. It's like a head and a body. Well, it does. It looks just like a rubber duck. So 7 billion kilometres in space, $2 billion, 10 years, time to rubber duck. So then we went into orbit for 3 months, looking for a landing site. And these are some of the images that we got from the surface. And the important thing to emphasise here is that this looks like a valley of a snowfield in Switzerland. Okay, not one component of this image is similar to anything on Earth. These boulders are not boulders, they are chunks of frozen gas. These boulders are frozen carbon dioxide, frozen carbon monoxide, frozen nitrous oxides. So it's not even waterized. So there is some waterized in the comet, but most of these are frozen gases. The actual surface of the comet is blacker than coal dust. Now we've enhanced the brightness and the contrast so I can show you an image. But the actual true colour is like soot or painted cartridge powder from a photocopier. Only 4% of the light actually gets reflected from the comet. So it's right here in the room with us, we actually couldn't see it. It's blacker than the black of this screen. That's not very black at all. But here in the background here, it's blacker and blacker than black. And even trying to see the thing as a human is impossible. Luckily, we knew that before we left. We knew there were very low light levels, we knew that the reflectivity of comets was very low, so we had extremely powerful and sensitive cameras. And this is why we can show you these images today. Again, so all these features, I won't go into a lot of detail because we don't have time, but every time we turn on the camera, we've got about 35,000 images now, we saw amazing things. This is, if we had an extremely powerful flash, this is what the true colour of the comet would look like. We used 17 different colour filters with the science camera, and this is a true colour rendition of what the comet actually looks like. So light browny colour, again, implying the sort of carbon chemistry, a lot of organic chemistry. This is the complex amino acids and sugars and fatty acids, which are comprised in this very primordial strange carbon chemistry of the early solar system. Another image. Okay, so again, this time we took a selfie, again, using the delay cameras. We're testing them before we deployed onto the surface. Again, just checking the cameras were working, which they were. Another nice view of the back of the solar panel, and the comet from the foreground instead of Mars. The last time we did it was at Mars. Okay, so this is where I mentioned there's been, 15,000 images have been taken, and we stitched them together, and we can make a 3D model of the comet with incredible resolution. Now, this is a wide-angle view, so we can zoom in down to centimeters. Because the resolution of the cameras is so powerful, we've actually mapped the 35 square kilometre surface area of the comet. Incidentally, it's 4 kilometres by 3 by 2. It's extremely small. And the surface area is 35 square kilometres, and the volume is 22 cubic millimetres. It's a very, very small object. It would fit nicely between the Harbour Bridge and the Anzac Bridge. You could easily put the comet in that space in Sydney, and that's the dimension. So this is the true rotation of the comet in space, and these images are being, again, stitched together by computer graphics. And we can actually zoom in and plan science and trajectories and navigation using all this information now. It's extremely powerful image processing computers. And so I don't think ever in the history of space exploration have we got this kind of information for scientists and trajectory navigation planners to use, because it makes the job very easy to have that kind of resolution. Okay, so I'm going to show you some of the more unusual features of the comet, which we've never seen on anything else in the solar system before. The really obvious ones are these very deep, very steep-sided, or actually almost cylindrical holes which are cut into the surface, like a sinkhole. And the best analogy I can use is a sinkhole in Guatemala, where basically it's just a cylinder which has just collapsed. And this is effectively what we've had on the comet, but in the opposite way. The cylinder has been blasted out, and the material has been popped off the surface, and there's a hole inside. So this is looking down on one of those holes. It's like a well. You can dig a well with cylindrical walls. It goes deep into the subsurface of the comet. By changing the contrast, we can see here that we've got these gas jets coming out. But what's actually happening here is the surface is quite hard, a bit like a shell of an egg. And inside is a soft volatile material that's wanting to evaporate when we get close to the sun. And when we do that, it builds pressure up inside the shell, and it pops a little bit of the shell off, and out comes the gas. So we've seen this all over the comet. So this is another example. This is another vent hole. And then we see that there's this ton of what is basically evaporated material from inside the comet, a gas, which has got quite enough when we got close to the sun, that it became temporarily a gas, then a liquid, and we see this liquid feature here as a remnant of the gas as it starts to solidify again. This is another example. This is where we have basically a vent hole with the corresponding cover on the right-hand side. So A is the manhole, I call it a manhole, and B is the cover of the manhole. So, because the comet is so small, it has 100,000th of a G. Okay, so the forces, the gravitational forces, are extremely low. And this is a 200-metre wide section of eggshell, I'll call it, which is just being pushed off by the pressure of the gas inside the comet. It's drifted across and it's landed a few centimetres away. And we can see the cap, basically, of the eggshell cover, the vent hole, just being popped off and the gas coming out as we get close to the sun. Now this shows you, these are 3 images taken by the orbital, and you can see one of these vent holes is going berserk. Okay, so it's 18 minutes between these 3 images, and in the middle of that 18 minutes, the vent hole has decided to spew out some gas from each quarter. So that shows that these vent holes are very dynamic, and they actually change the rotation speed of the comet. The comet rotates at every 12.4 hours, it's about twice as fast as the Earth's rotation. But we've had a variation of plus or minus 7 minutes in the rotation rate of the comet, caused by the thruster effect of the gas jets coming off the surface of the comet. Because it's small enough that we can actually change the speed of the rotation. We've seen these strange features where we've got sand dunes on the surface of the comet. Now, there's no atmosphere on the comet, it's too small. It's way too small. But we're still seeing evidence of wind-blown features. And here as well, we see what we call these wind tails behind, they're not boulders, they're frozen chunks of gas. Okay. But we've got these features of what appears to be wind features. Now, what this is, in fact, is these venting from these wells, these sinkholes, actually leave trails of material behind. So we have a temporary atmosphere while it's outgassing this. While it's outgassing like this, it leaves some residue behind. And that's the evidence of this pretend atmosphere we have. Okay, the neck is cracked. So back to the model. Here on the neck, here, there is a big crack. And that's all proof of the fact that the 2 bodies stuck together very gently under gravity. And there is a chance that they could separate. Now, the long name of the comet, 67P, is called Churyumov-Berezamenko. It was discovered by two Ukrainian observers back in 1969, astronomers back in 1969, and there were two of them. So luckily, if the comet does break in two, we can call the head Churyumov and the tail Berezamenko. So this is a big crack, and there is a chance it could break in two, with gas pressure or gravitational forces. Now this is showing, again, it really is a comet. We've got gas and dust blasting off the surface of this thing all over the place. So it's not an asteroid. Asteroids do not evaporate, they do not have any emissions, or very, very, very few. Nothing like this. We have to fly Rosetta in orbit around this body while it's blasting out this gas. So at the moment, we're actually 1,500 kilometers away from the comet. But the forces from these blasts are so strong against the solar panels, it's a bit like a sounding boat. In fact, we don't need to be that far away. We've done it for a special reason just recently. But normally we have to be about 300 kilometers away during this active phase. When it gets calm, we come back in again down to within 10 kilometers. So we've been very close when we first got to the comet, and as the 10 more active, we have to move away because of the gas and dust. Okay, so what's on the surface? We've got these incredibly complex mass spectrometers which can do incredibly high resolution measurements. Here we've got silicon, carbon monoxide, nitrogen gas, ethene, it's called, all these have the same atomic mass, with very, very small variations. So because we've got such a good mass spectrometer on board, we can actually stretch the resolution of the mass measurement to be 28 plus or minus 0.02 on these measurements here. So even though all these molecules and elements have effectively the same mass, we've got such a good mass spectrometer on board, we can actually separate and actually get the true ratio of these similar mass elements and molecules to make these measurements of the comet. And they all smell disgusting. So we've been able to go back and get these ratios of these molecules and put them in a lab in a big dish and smell it. Now I can't do that tonight because it's quite difficult getting the chemistry, but I've done it at several schools, and the smell is unbelievably disgusting. Does anybody here know the smell of butyric acid? It's like baby vomit. It's like congealed lactose with acid, and it's a revolting smell. So when I told you that we were made, water and the amino acids that formed the very first life on Earth, and eventually came us. When they say that gels are made of sugar and spice and everything nice, it's not true. They're made of smelly electrons. And this is proof. The mass spectrometer, we can actually create all this chemistry in the lab and get a first-hand smell of the comet. This is an image showing the relative brightness of the comet against Enceladus, which is one of the moons of Saturn, Earth that we know, and the moon. So imagine the cameras on Rosetta are 1 million kilometers away from each of these bodies, and this is the relative brightness of the comet. This is the relative brightness of what the comet would be, but I've actually had to magnify it by 100 times, because it is so dark, we wouldn't see anything. So again, I'm just trying to emphasize how black, how small. It has no atmosphere that we can use for deceleration when we're doing the landing. It is the most impossible object you could possibly imagine. And a distance of almost 1 billion kilometers when we first found it. So try to go into orbit and land it. But we did. So that was the challenge of the Rosetta missions. All these parameters made it incredibly difficult, which is why the NASA guy said it was a difficulty and sort of difficult. Okay, so if you want to hear what the sound of the comet is, the atmosphere, this tenuous atmosphere from the evaporation of the material from the comet forms plasma. And the gas gets ionized by the ultraviolet light from the sun. And it forms basically a charged gas, which is modulated by the solar wind from the sun. So it's all a bit complex, but there's a mechanism where the gas coming off is having oscillations caused by electrostatic forces. And this, so it's actually very low frequency. We speeded it up 10,000 times, put through a speaker. And this is what the sound of the comet sounds like. So those oscillations, it sounds like a flying bumblebee, I don't know if you know the music. They've got no idea what's causing this. This was measured outside the asteroid belt before the comet was being activated by the heat from the sun. This is a kind of noise or interaction we expect close to the sun, where there's a lot of energy. But this is outside the asteroid belt when we first discovered this. And it's an extremely complex interaction, trying to understand how this kind of sound can develop from what is effectively an extremely cold, non-volatile comet at those distances. So that every single thing that we turn on, every single instant we turn on, we find something we don't expect. And this is the joy of interplanetary expeditions. They're like on this ship in America. Every single thing we see is unexpected. And this is just another example. Okay, so we've been in orbit, we've been doing lots of science. Now we want to do a landing. Okay, so we've been in orbit for 3 months, looking for a landing spot. Now this is how we planned the landing. This is what we wanted to do. So Rosetta's been carrying the little Philae, the little lander, for 10 years. We're flying over, remember I showed you the deployment? We're flying over the surface at a height of 22 kilometers. We pop the lander off at about 18 centimeters per second, about 1 kilometer an hour. And it's actually effectively stationary above the top of the comet. We then start drifting down at 1 meter per second, and it takes 7 hours for the spacecraft to get down to the surface at 3 kilometers an hour. And as we're going down, we've got these two harpoons here, which were meant to fire, and those two red lines are showing the wires as we go in under the surface. We're meant to hold on to the comet to stop it from rebounding, but they didn't fire. The nitrocellulose, which is a bit like a bullet, the chemistry had been changed by 10 years in space, at minus 300 degrees, 75 kilowatt radiation, in a hard vacuum. Now, we didn't test that before we launched, because we wanted to put these two harpoons into a vacuum chamber for 10 years, at minus 300 degrees, to 75 kilowatt radiation. We would never have a mission. So that was a risk that we took. We made 2 of them, but both of them failed. So what happened? This is a video of the landing site. It's a bit boring, actually. I might just come through that. Okay, so this is the landing site on the edge of the comet. So, just right at the top here is where we decided to do the landing of Philae. That turned out to be the flattest part of the entire comet, which is not very flat. You can see it's covered in boulders, but very nice. And 50% of this surface area was unsuitable for landing, because it would tip over the lander. But we carried it all that way, we're going to put it down on the bottom. Okay, so this is in fact the flattest area that we can find. Okay, so this is what we wanted. We wanted a landing on a nice flat open plane with half the sky above and surface of the comet below, illuminated by the sun. Okay, so we wanted to turn on the panoramic cameras and get 360-degree field of view, with also stereoscopic cameras so that we can get depth of field. Now, this was the true deployment. This is using the scientific camera from Rosetta looking down to the comet from an altitude of about 30 kilometers, zooming in on the little lander as it's coming down. Each one of these moves about 5 minutes a month, and it's stripping down 1 meter per second down to the surface. In the background of this image is the comet, which you can't see it. But because we're going to look at the lander, we had to set the brightness level to see the lander, we couldn't see the comet. So this just shows you these huge contrast ratios. And if we wound up the brightness to see the surface of the comet, this line here would completely saturate the whole image. Okay, so this is the image that's taken as looking from a camera looking directly down on the lens. So if you have a little camera looking down, this is from 60 meters, 50 meters, 38, 28, 18, and 9 meters above the surface. So this is a descent sequence of a series of images as we approach the surface from a camera on Philae. So these are the very first images we got from little Philae, and everything's working. You'll hear that's the name of the landing site that we're going for. So these are millimeters to centimeters in size. These little grains of material. Okay, the first confirmation we hit the surface, I told you about the microphones in the feet, was this sound. That was hitting the surface. 3 microphones in the feet. That was the audio signal confirming we had physical contact with something. It wasn't the surface. The problem was we danced. And this image here shows us again looking down from Rosetta onto the surface, and you see this puff of gas. This is a dust cloud, and the shadow formed by Philae hitting the surface, but it wasn't left behind. You can see this is where we wanted to land. The landing was absolutely perfect in terms of trajectory. It was within 15 meters of the green square, which is where we wanted to land. This is a deployment from 22 kilometers high. We got within 15 meters of what we wanted. But unfortunately, the lander didn't stay behind. It bounced off somewhere, and it wasn't there. So we had to find it. And this, I think, is the most amazing image, probably in the history of space exploration. Because this shows, again, looking down on the surface of the comet, which is blacker than coal dust, as I keep telling you. You have to bring up the brightness to be able to see the surface features, and pull out the image of little fillet drifting across the surface. This is a sequence of images 5 minutes apart, showing fillet drifting across the surface on an altitude of 30 kilometers, looking down at a little 1 square meter little lander. And this is a touchdown. Now, this is the before image, and this is the after image. So you can see there are no footprints there, but there are 3 footprints there. So exactly where we wanted to find it, it should have been there, but you could just see the 3 footprints. Now that image was taken at 1543. Okay? At exactly the same time, we looked around, and here in the shadow, on the right-hand side, was a little fillet drifting out of the field of view of the image at the same time. So in that same instance, instead of being there, it was there. But it was actually flying. It had not touched down, it had bounced off. It took 1 hour and 50 minutes to come back down again. And we actually travelled 1.3 kilometres. We actually hit the edge of the crater during that time as well. So it was a really, really bizarre, crazy landing because an afternoon's been flying all the time. This is a video simulation showing that. So this is the deployment of the lander from Rosetta. And then there's an evasive maneuver so it doesn't crash into the comet. The little lander continues down with the comet rotating underneath. So we have to calculate all these things and pre-calculate the timing to get to this point where the red dot is. Now we've exaggerated the area there. It's actually only about 15 metres, but look here, it's several hundred. And we bounced. Okay? So we went off like this, and we actually hit a little ridge here. This one here. There's where we hit the ridge. And we came down in a crevice on the far side of the landing spot. Unfortunately, 75% of the spacecraft is covered in shadow in terms of time. So it landed on the side of this little crevice, but only 25% of the time of those 12 hours of rotation I was going in is in sunlight. And 75% of the time it's in shadow. So that means we don't get the solar power that we needed in terms of the lander back on again after the first land stage. Okay, so that's a small bit. A bit of a timing problem, so wait for this to be. Okay. Isn't that just classic? Remember. This happened only once before. Okay, I'm going to have to restart on sorry.
This might
Where were you when all this was happening, Warwick? Were you here or over in?
I was in Belgium, Germany. Yeah.
You were there?
The people who built the spacecraft were invited to the landing.
How was the atmosphere there?
It was like my fingernails. They're still going back. No, it was the most incredible thing. You never possibly imagine it. It's okay, so this is the image that we got when we were on the surface. So after the bouncing, we turned on the panoramic cameras, and this is the field of view that we got from the 7 cameras around the lander. None of them we could recognise very easily until we stitched the images together. We got this one image, or 2 images, where the sunlit side of the crevice was showing us incredible detail of the surface. So this is the landing gear. Philae landed, I was telling you many times ago, I was putting the accelerometers on it, now on the surface of the comet. So the landing gear at this point was 17 years old, touching a surface which is more than 4.6 billion years old. It's the oldest surface of anything that's ever been touched in the solar system. Surface temperature, just for instance, was minus 145 to minus 180 degrees, so it's extremely cold at the moment of landing in August, 12th of November 2014. It's just interesting to do these comparisons. 17-year-old lander touching a 4.6 billion-year-old comet. This is an interesting comparison of the surfaces. And so we've now got this surface image of a comet, an asteroid, the Moon, Venus, Mars, Titan, the Moon of Saturn, and Earth. What always surprises me in this image, by chance, is the fact that only 2 of these images come from NASA. And NASA is responsible for landing on a comet. On an asteroid, sorry. ESA on the Comet and the landing on Titan. The Russians did the landing on Venus, so it's got quite surprised when I actually saw this image to realise that, oh, NASA's actually only done 2 of these images. Surprising. Anyway. Okay, so this is a graphic showing where the lander is on the surface. So it's squished in a small crevice, tilted at 80 degrees. Now, unfortunately, on exactly the same day that we landed on Philae, Kim Kardashian decided that they're crevice as well. So there we are. Philae landed in the crevice, and here also the internet went crazy putting this image of Philae landing on Kim Kardashian's area. So unfortunately, we can't look very bad. These are the image credits of all those images I've been showing you from the European Space Agency and the contributing scientific institutes, and that's the end of my presentation. Thank you very much.